Special relativity is a theory of space and time developed by Albert Einstein in 1905. Before the development of special relativity, physicists believed in an absolute space and time, which means that the laws of physics were the same for all observers, regardless of their relative motion. However, experimental evidence began to suggest that the speed of light was constant and independent of the motion of the observer. This discrepancy led Einstein to develop a new theory that would reconcile the observations with the principles of physics. In 1905, Einstein published his paper on the electrodynamics of moving bodies, which laid out the framework for special relativity. The paper introduced the idea of the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion relative to one another. This principle contradicted the previously accepted notion of absolute space and time, and its implications were far-reaching. Special relativity challenged the way physicists thought about space and time and led to a new understanding of the nature of reality. The theory provided a unified framework for describing the behavior of particles at high speeds and helped to resolve long-standing problems in physics. In the years following the publication of Einstein's paper, special relativity was met with skepticism and criticism from some members of the scientific community. However, the theory was eventually confirmed through numerous experiments, and its implications continue to be explored and applied in fields such as particle physics, cosmology, and engineering. Today, special relativity is recognized as one of the most important and revolutionary ideas in the history of science. The principle of relativity is a fundamental postulate of special relativity, which states that the laws of physics are the same for all observers in uniform motion relative to one another. This means that there is no absolute state of rest, and all motion is relative. One of the most profound consequences of the principle of relativity is the invariance of the speed of light. According to special relativity, the speed of light in a vacuum is constant and independent of the motion of the observer or the source of the light. This means that no matter how fast an observer is moving, they will always measure the speed of light to be the same value. The invariance of the speed of light has significant implications for our understanding of the nature of space and time. In particular, it implies that time and distance are relative and depend on the motion of the observer. This effect is known as time dilation and length contraction, and it is one of the key predictions of special relativity. One of the most important experiments to support the theory was the Michelson-Morley experiment, which demonstrated that the speed of light is the same in all directions. Today, the principle of relativity and the invariance of the speed of light are recognized as some of the most profound and revolutionary concepts in modern physics, and they continue to be studied and applied in a wide range of fields. The twin paradox is a thought experiment that illustrates the effects of time dilation in special relativity. The experiment involves two identical twins, one of whom remains on Earth while the other travels through space at high speed. According to special relativity, time will appear to move more slowly for the traveling twin, so when they return to Earth, they will be younger than their twin who remained on Earth. While the twin paradox may seem paradoxical at first glance, it is actually a straightforward consequence of the principles of special relativity. Time dilation occurs because of the relative motion between the observer and the source of the clock, and it is a well-established phenomenon that has been confirmed by numerous experiments. The equivalence of mass and energy is another profound concept in special relativity. According to Einstein's famous equation, E is mc2, mass and energy are interchangeable, and the total energy of a system is equal to its mass times the speed of light squared. This means that even small amounts of mass contain a tremendous amount of energy, as seen in nuclear reactions and other high-energy processes. The equivalence of mass and energy has been confirmed by numerous experiments and has significant implications for our understanding of the universe. It explains how stars produce energy through nuclear fusion, and it is the basis for the development of nuclear power and weapons. The resolution of the twin paradox and the equivalence of mass and energy are two of the most fascinating and significant concepts in special relativity. They illustrate the profound ways in which this theory has transformed our understanding of the universe and continue to inspire new research and discoveries in physics. In special relativity, the speed of light is constant for all observers, regardless of their relative motion. This means that the laws of physics must be the same for all observers, regardless of how fast they are moving. The Michelson-Morley experiment was a crucial experiment that helped to confirm the principles of special relativity and the invariance of the speed of light. The experiment involved measuring the speed of light in different directions using an interferometer in order to detect the Earth's motion through the hypothetical ether that was believed to permeate all of space. However, the experiment found that the speed of light was the same in all directions, regardless of the Earth's motion. This result was difficult to explain using classical physics, but it was consistent with the principles of special relativity. The Michelson-Morley experiment helped to usher in a new era of physics, in which the classical concepts of space and time were redefined in light of the principles of special relativity. The experiment was a crucial milestone in the development of special relativity, and it remains an important historical moment in the history of science. Special relativity has had a profound impact on modern physics and our understanding of the universe. It has led to many important discoveries and has had numerous practical applications in fields such as nuclear physics, particle physics, and astronomy. One of the most famous applications of special relativity is the development of nuclear energy and the atomic bomb, which rely on the equivalence of mass and energy, and the famous equation E=2. Other practical applications of special relativity include the use of particle accelerators to study the behavior of subatomic particles, the development of GPS technology, and the study of high-energy astrophysics, such as black holes and supernova. To help understand the principles of special relativity, many physicists have used thought experiments and visualizations. One of the most famous thought experiments is the twin paradox, which has been mentioned before. Other visualizations used to understand special relativity include the light clock, which involves a clock that is based on the time it takes for light to bounce between two mirrors, and the space-time diagram, which is a graphical representation of the effects of time dilation and length contraction on an object in motion. Overall, special relativity has had a profound impact on modern physics and our understanding of the universe. Its principles continue to be studied and explored by physicists to this day, and its practical applications continue to be developed and refined. Despite its widespread acceptance and numerous successful predictions, special relativity has also faced a number of misconceptions and criticisms over the years. Here are a few of the most common. Relativity is just a theory. While it is true that special relativity is a scientific theory, it is not just a guess or a hunch. The theory has been extensively tested and has consistently been shown to accurately describe the behavior of the universe. Relativity only applies to objects traveling at near the speed of light. While the effects of special relativity become more pronounced at higher speeds, the theory applies to all objects, regardless of their speed. Relativity violates common sense. The effects of special relativity can sometimes seem counterintuitive, but they are based on rigorous mathematical and experimental evidence. Relativity has been disproven by experiments. Despite some attempts to disprove special relativity, no experiment has ever conclusively shown the theory to be incorrect. Relativity contradicts classical physics. While special relativity does differ from classical physics in some ways, it does not contradict it. Rather, it provides a more accurate and complete description of the behavior of the universe. In response to these misconceptions and criticisms, physicists have continued to study and refine the principles of special relativity. They have also worked to communicate the theory in a way that is accessible and understandable to the general public. By doing so, they hope to promote a better understanding and appreciation of the fundamental principles that govern our universe.